Consider a simple measuring tape, a universal symbol of fixed distance. Now, imagine using that tape to measure something not only moving at unimaginable speeds, but also, in its very essence, expanding. This isn't a thought experiment in abstract physics, it's the fundamental challenge at the heart of cosmic measurement. For millennia, humanity gazed into the night sky, a velvet curtain adorned with static, unyielding points of light. We drew constellations, wove myths, and believed the stars to be fixed jewels on a crystalline sphere just beyond our grasp. But what if everything we thought we knew about that celestial canvas was a profound, beautiful illusion? What if those fixed points were in fact rushing away, their light taking eons to reach us, charting a universe far grander and more dynamic than any ancient philosopher dared to dream? The quest to measure the cosmos is far more than an academic exercise. It's a scientific odyssey that has systematically dismantled our geocentric biases, shattered perceived limits, and redefined our very understanding of reality itself. Each discovery of cosmic distance has not merely provided a new number, but fundamentally altered our perspective on humanity's minuscule yet miraculous place within an infinite tapestry. We embarked on this journey believing our world was the universe's anchor, its size confined to a few thousand earthly miles. Today, our instruments reveal an observable universe that stretches an astounding 93 billion light-years across. In this documentary, we will trace this breathtaking evolution of understanding. We will meticulously unpack the ingenious cosmic yardsticks, from the precise geometry of parallax and the rhythmic pulse of Cepheid variable stars to the universal stretch of redshift and the profound echoes of the Big Bang. Each method, a revolutionary step, pushed back the boundaries of the known, forcing us to recalibrate our entire worldview. If you're ready to scale the universe with us, hit that like button and subscribe to Terran for more cosmic revelations. Prepare yourselves. We begin. From the very first flicker of firelight in the primordial night, humanity's gaze has been drawn upward to the star-dusted canvas stretching endlessly above. Yet, for countless millennia, this vast celestial tapestry remained an enigma, its true dimensions veiled by the limitations of our perception and the profound biases of our own existence. The earliest attempts to fathom the cosmos were not rooted in precise measurement, but in philosophical contemplation, weaving myth and meaning into the observed patterns of light. The universe, in these nascent understandings, was a dome, a sphere, a tangible ceiling just beyond the reach of our immediate world. Its size was assumed, not calculated, intimately tied to the perceived scale of human experience. This foundational, Earth-centric view crystallized most vividly in the intellectual crucible of ancient Greece. Philosophers like Aristotle, with unparalleled intellectual rigor, constructed a universe both elegant and rigidly defined. At its heart lay a perfectly spherical Earth, motionless, the undisputed center of all creation. Around it, in concentric perfection, orbited crystalline spheres, each carrying a celestial body: the moon, the sun, the known planets, and finally, the outermost sphere, studded with the fixed stars. This Aristotelian cosmos was finite, comprehensible, and profoundly human-centered, its boundaries no more than a few thousand miles from our terrestrial home. The motions observed from the daily arc of the sun to the wandering paths of the planets were believed to be perfect circles, reflecting divine harmony. Yet, even within this geometrically sublime model, observations presented a stubborn challenge. The planets, those enigmatic wanderers, did not move in simple, perfect circles. Their paths were irregular. They would occasionally slow, reverse direction in a perplexing retrograde motion, and then resume their forward journey. To reconcile these perplexing observations with the prevailing philosophical ideal of circular orbits, Claudius Ptolemy, in the 2nd century AD, crafted an elaborate and remarkably enduring system. His monumental work, the Almagest, introduced a complex architecture of epicycles and deferents, smaller circles upon larger circles, to meticulously map the convoluted paths of the planets. This geocentric model, though intricate and ultimately incorrect, was a triumph of mathematical ingenuity. it could accurately predict planetary positions for over 1400 years, effectively defining the known universe as a series of nested, perfectly interlocking celestial mechanisms still fundamentally limited in scale, bounded by the sphere of fixed stars. The idea of truly vast, empty distances between these spheres was simply not part of the paradigm. The heavens were a compact, ordered clockwork. While the ancients struggled with the heavens, a different kind of measurement was taking shape on Earth, laying crucial intellectual groundwork. Centuries before the heliocentric revolution, the Greek polymath Eratosthenes, through a remarkably simple yet profound experiment, accurately calculated the circumference of Earth. By comparing the angle of shadows cast by the sun at noon in two different cities on the same day, he deduced the curvature of our planet. This was a monumental achievement, not directly measuring cosmic distance, but demonstrating the power of geometry and observation to quantify the immense. It offered a crucial psychological shift. If Earth itself could be measured, why not the celestial spheres? Indeed, another brilliant Greek, Aristarchus of Samos, took up this challenge. Using geometry, he attempted to calculate the distances to the moon and the sun. By observing the angle between the moon and the sun during lunar phases, and the Earth's shadow during eclipses, he made the astonishing deduction that the sun was vastly larger than Earth, and therefore, by a stroke of philosophical insight, likely the centre of the solar system. His calculations, though hampered by the technological limitations of precisely measuring the small angles involved, which led to significant underestimations of the actual distances, were conceptually revolutionary. He posited a heliocentric model nearly 2 millennia before Copernicus, a testament to raw intellectual courage. His efforts showed that the universe could be measured, even if the tools weren't yet sharp enough to carve out its true scale. The cosmic stage remained largely unchanged until the 16th century, when Nicholas Copernicus rekindled Aristarchus's radical idea. His heliocentric model, placing the sun at the centre of the solar system, was not immediately embraced for its groundbreaking philosophical implications, but for its elegant mathematical simplicity. It swept away Ptolemy's cumbersome epicycles, explaining retrograde motion as a natural consequence of Earth and other planets orbiting the sun at different speeds. This shift, however, came with a profound unspoken implication for the scale of the cosmos. If Earth was orbiting the sun, and we didn't observe any apparent shift in the positions of the fixed stars over the course of a year, a phenomenon known as stellar parallax, then those stars had to be incredibly distant. Far, far more distant than anyone had ever conceived, pushing the boundaries of the universe from a mere few million miles to an unimaginable, unquantifiable abyss. The lack of observable parallax was, paradoxically, the first clue to the truly immense size of the universe. The stage for further expansion was then meticulously set by Tycho Brahe, whose unparalleled precision in naked-eye astronomical observations in the late 16th century provided the most accurate data of his time. His meticulous records, though still within a geocentric framework modified by himself, were instrumental in what followed. Crucially, his observation of a supernova in 1572, Tycho's supernova, demonstrably in the supposedly immutable celestial sphere of stars, shattered the Aristotelian notion of a perfect, unchanging cosmos beyond the moon. The heavens were not static, they were dynamic, suggesting a universe less perfect, perhaps less confined, and certainly more mysterious. Tycho's student Johannes Kepler inherited his vast treasure trove of data. Rejecting circular orbits for ellipses, Kepler formulated his 3 laws of planetary motion in the early 17th century, providing a mathematically precise description of how planets moved around the Sun. These laws allowed astronomers to calculate the relative distances of planets from the Sun with unprecedented accuracy, establishing the astronomical unit AU, the average distance from Earth to the Sun, as a foundational, albeit still relative, cosmic ruler. But while Kepler's work mapped the solar system with astonishing fidelity, it still lacked an absolute scale. We knew the planet's distances relative to Earth, but not how many miles or kilometers constituted 1 AU. The entire system could still be scaled up or down, much like a blueprint without a scale bar. The final, decisive blow to the old cosmology came with Galileo Galilei and his pioneering use of the telescope in the early 17th century. His observations of Jupiter's moons orbiting Jupiter the phases of Venus mirroring those of the Moon around the Sun, and the myriad of previously unseen stars in the Milky Way provided irrefutable observational evidence for the Copernican model. Galileo didn't measure the distances to stars, but he revealed a solar system far richer and more dynamic than imagined, effectively decentralizing Earth in a tangible, verifiable way. The universe, through his lens, became conceptually larger, a place teeming with celestial bodies, hinting at a scale that still defied direct measurement, but was undeniably grander than any previous era had dared to contemplate. We were moving from a universe that felt small to one that felt vast, driven by philosophical shifts and increasingly precise observations that challenged ancient dogma. The challenge now was to develop the tools to quantify this new, expansive reality. The intellectual triumphs of Copernicus and Galileo had shattered the crystalline spheres, casting our planet from the cosmic center. Yet, even with a sun-centered solar system firmly established, the universe beyond remained largely unquantified. We knew the planet's relative distances, but the leap from Earth to the nearest star felt like an unbridgeable chasm. The vastness was conceptual, not yet numerical. The crucial missing piece was an absolute scale for the solar system itself, a precise measurement for the astronomical unit. Without knowing the exact distance from Earth to the Sun, all other relative distances remained floating, untethered to a tangible cosmic ruler. The first audacious attempts to pin down this fundamental distance involved observing the transit of Venus across the face of the Sun. These rare celestial events, occurring in pairs separated by over a century, offered a unique opportunity for global collaboration. By coordinating observations from widely separated locations on Earth, astronomers could use the principles of parallax, the apparent shift in an object's position when viewed from different angles, to triangulate the Sun's distance. The logic was elegant. Venus would appear to cross the Sun at slightly different points for observers on opposite sides of Earth, creating a tiny, measurable displacement. This tiny angular shift, combined with the known baseline distance between the observers, could mathematically unlock the precise scale of the solar system. One of the most ambitious scientific expeditions in history was launched for the 1761 and 1769 transits of Venus. Scientists, including the intrepid James Cook, sailed to remote corners of the globe, enduring unimaginable hardships, disease, and perilous voyages to capture these fleeting moments. Their collective, painstaking efforts, though fraught with observational challenges and measurement uncertainties, yielded the first reasonably accurate value for the astronomical unit. By the early 19th century, thanks to these heroic endeavours, humanity had a firm numerical grasp on the scale of our solar system, approximately 93 million miles or 150 million kilometres. This was a monumental achievement, transforming our local cosmic neighbourhood from a relative blueprint to an absolutely scaled reality. Now, armed with this foundational unit, the next great challenge loomed: measuring the distances to the stars themselves. The concept of stellar parallax, a direct consequence of Earth's annual orbit around the Sun, had been understood since antiquity. As Earth travels from one side of its orbit to the other, a nearby star should appear to shift slightly against the backdrop of more distant, seemingly fixed stars. Imagine holding your thumb out and closing one eye, then the other. Your thumb appears to jump. Earth's orbit provides the two eyes and the baseline. The greater the apparent shift, the parallax angle, the closer the star. Conversely, the smaller the shift, the more distant the star. The challenge, however, was the minuscule nature of this shift. If stars were truly as distant as the Copernican model implied, their parallax angles would be incredibly small, far too small for naked eye observation or even the early telescopes to detect. The lack of observable parallax for centuries was precisely why many resisted the heliocentric model, arguing that if Earth moved, such shifts should be seen. The technological hurdle was immense. To detect these minute angular displacements, astronomers needed telescopes of unprecedented precision and stability, coupled with meticulous observational techniques. The parallax angles were measured not in degrees but in arcseconds, a unit so tiny that 1 arcsecond is equivalent to the width of a human hair viewed from 10 miles away. It required instruments capable of detecting shifts often less than a single arcsecond. For centuries, the attempt to measure stellar parallax was a frustrating, often humbling endeavour. Many brilliant astronomers tried and failed, their instruments simply not sensitive enough to capture the ephemeral wobble of a distant star. Then, in a remarkable scientific race in the 1830s, 3 astronomers, working independently across different continents, finally achieved the impossible. Friedrich Bessel, a German astronomer, was the first to announce a successful measurement in 1838. He meticulously observed 61 Cygni, a relatively nearby star, over many months. His patience and the precision of his heliometer, an instrument designed for measuring small angles, paid off. He detected a parallax of about 0.31 arc-seconds, placing 61 Cygni at a distance of approximately 10.4 light-years. This was the first direct empirical measurement of the distance to a star beyond our Sun. It shattered the old cosmological barrier, revealing a cosmos where even the nearest stars were light-years away, an unfathomable void separating stellar neighbours. Soon after Bessel's breakthrough, Thomas Henderson in South Africa measured the parallax of Alpha Centauri, finding an even larger shift of 0.75 arc-seconds, indicating it was even closer at about 4.3 light-years. And in Russia, Otto Struve measured the parallax of Vega. These simultaneous triumphs were revolutionary. They not only confirmed the heliocentric model beyond any doubt, but also provided the first tangible numerical scale for interstellar space. The universe was no longer just the solar system. It was a sprawling collection of stars, each separated by immense, previously unimaginable distances. The concept of the light year began to gain traction as the natural unit for these new, grander scales. The method of stellar parallax, though conceptually straightforward, had practical limitations. It was incredibly difficult to measure, only effective for the very closest stars. As distance increased, the parallax angle rapidly diminished, becoming too small to detect even with the most advanced telescopes of the era. By the late 19th and early 20th centuries, ground-based parallax measurements could reliably reach out to about 100 light-years, encompassing a relatively small bubble of space around our Sun. This was a magnificent expansion from the solar system, but it was still just a tiny speck within what astronomers suspected was a much larger galaxy and perhaps an even vaster universe. Despite its limitations, parallax was and remains the bedrock of the cosmic distance ladder. It is the only direct, model-independent way to measure distances to stars. All other methods for greater distances are calibrated against parallax measurements. It's the foundational rung on the ladder, the ultimate standard against which all other cosmic yardsticks are compared and validated. Without Bessel's pioneering work, the entire edifice of modern cosmic distance measurement would lack its empirical anchor. The painstaking work of early parallax astronomers highlighted the sheer emptiness of interstellar space. Their measurements revealed that even within our own galaxy, stars were not packed densely together, but were solitary beacons scattered across vast, dark gulfs. This realization began to shift our mental image of the cosmos from a relatively compact arrangement to one dominated by emptiness, a theme that would only grow in significance with subsequent discoveries. The universe was not just big, it was empty. This profound emptiness was not a void of nothingness, but an expanse of distance, a canvas awaiting the next brushstrokes of cosmic revelation. The expansion of the known universe, from the local solar system to a few hundred light-years, was a testament to the scientific method, observation, hypothesis, and meticulous measurement. It proved that human ingenuity, armed with increasingly sophisticated instruments, could unravel the deepest secrets of cosmic scale. But the universe was clearly much, much larger. Our own Milky Way galaxy, a hazy band of light across the night sky, remained an unquantified mystery. Was it a distinct island universe of stars, or simply the sum total of all existence? To answer this, and to push the boundaries of knowledge even further, a new cosmic ruler would be needed, one capable of reaching far beyond the limits of parallax. The next chapter in our quest for cosmic scale would depend on a different kind of stellar flicker, a rhythmic pulse that promised to unlock the true grandeur of our galaxy and beyond. The triumph of stellar parallax had given us the first true measure of interstellar space, extending our cosmic reach hundreds of light-years. Yet this was merely a glimpse into our immediate stellar neighbourhood. the vast hazy band of the Milky Way sprawling across the night sky remained an unquantified enigma. Was it a colossal collection of stars forming a distinct island universe, with our solar system nestled somewhere within? To truly map our galaxy and peer beyond its perceived limits, astronomers needed a new kind of cosmic measuring stick, one that could transcend the relatively short reach of parallax and probe the depths of hundreds of thousands, even millions, of light years. This breakthrough arrived in the early 20th century, born from the meticulous observations of variable stars. Henrietta Swan Leavitt, a diligent astronomer working at the Harvard College Observatory, was tasked with cataloguing variable stars in the Magellanic Clouds, two small satellite galaxies visible from the southern hemisphere. Among these, she focused on a particular class of pulsating stars known as Cepheid variables. These stars exhibit a peculiar and consistent behaviour. They rhythmically brighten and dim over a period of days or weeks, like cosmic lighthouses blinking in the dark. Leavitt's groundbreaking discovery came in 1908. After painstaking analysis of hundreds of photographic plates, she noticed a profound relationship. The brighter a Cepheid variable star intrinsically was, the longer its pulsation period. This wasn't a random correlation, it was a precise mathematical link. A star that pulsed every few days was intrinsically fainter than a star that pulsed every few weeks. This relationship, which became known as the period-luminosity relationship, was revolutionary. It meant that by simply observing how quickly a Cepheid pulsed, astronomers could determine its absolute luminosity, its true intrinsic brightness, regardless of how faint it appeared from Earth. This was the critical insight. Imagine two identical light bulbs, one close by and one far away. The distant bulb appears dimmer, but you know both bulbs have the same wattage. By comparing their apparent brightness, you can calculate how far away the dimmer distant bulb must be. Cepheids offered this exact principle for stars. If we knew a Cepheid's true wattage, absolute luminosity, from its pulsation period, and we could measure its apparent brightness from Earth, a simple inverse square law calculation could reveal its distance. Cepheid variables became the universe's first reliable standard candles, objects with a known intrinsic brightness that could be used to calculate cosmic distances. However, a crucial step remained. Calibrating the period-luminosity relationship in absolute terms, Leavitt had established the relative brightness of Cepheids. But their absolute luminosities still needed to be anchored to a known distance. This is where the earlier work on parallax became indispensable. Astronomers painstakingly searched for Cepheids close enough to Earth to have their distances measured directly through stellar parallax. Once a few nearby Cepheids had their absolute distances, and consequently their absolute luminosities precisely determined, Leavitt's period-luminosity relationship could be fully calibrated. This established Cepheids as a powerful new rung on the cosmic distance ladder, extending our reach far beyond the limits of parallax. The implications were immediate and profound. Einar Hertzsprung, building on Leavitt's work, was among the first to use Cepheids to estimate the distances to nearby star clusters. Then, in 1918, Harlow Shapley employed Cepheids to map the true scale of our own Milky Way galaxy. Before Shapley, many astronomers believed the Sun was near the centre of the galaxy, and the galaxy itself was relatively small, perhaps a few tens of thousands of light-years across. By observing Cepheids within globular clusters, dense spherical collections of hundreds of thousands of stars found in the galactic halo, Shapley calculated the distances to these clusters. He noticed a peculiar distribution. Globular clusters were not centered on the Sun, but rather on a point far away in the direction of Sagittarius. Shapley's daring conclusion, though initially met with skepticism, was that the Milky Way was far larger than previously imagined, a vast disk of stars approximately 100,000 light-years across, with the Sun located about two-thirds of the way out from the galactic centre. This was a monumental scale shift. Our solar system was no longer the centrepiece of the galaxy. It was an unremarkable speck in its outer suburbs. The universe had just grown by orders of magnitude, now encompassing an entire spiral galaxy, a colossal island universe of stars, gas and dust. This revelation dramatically pushed back the boundaries of the known world, forcing humanity to confront a new level of cosmic humility. Yet, even with this galactic mapping, a heated debate persisted. a question that would define early 20th century cosmology, were the spiral nebulae, fuzzy spiral-shaped patches of light observed through telescopes, simply gas clouds within our own Milky Way, or were they entirely separate galaxies, other island universes like our own? This was the great debate of 1920, famously pitting Shapley against Heber Curtis. Shapley argued the nebulae were local, while Curtis contended they were extragalactic. Without a way to measure distances to these elusive nebulae, the debate remained unresolved, anchoring the universe's known extent to the boundaries of the Milky Way. The resolution to this debate, and the next monumental leap in cosmic scale, would once again fall to Cepheid variables. Edwin Hubble, using the then revolutionary 100-inch Hooker telescope at Mount Wilson Observatory, embarked on a meticulous search for Cepheids in the Andromeda Nebula. The Hooker telescope offered unprecedented light-gathering power, allowing Hubble to resolve individual stars in what was previously thought to be an undifferentiated cloud. In 1923, he found them, faint, pulsating Cepheid variables in Andromeda. Applying Leavitt's period-luminosity relationship, now calibrated by parallax, Hubble calculated the distance to Andromeda. His results were staggering. Andromeda was not a cloud within our galaxy, but an independent galaxy located over 2.5 million light-years away. This single measurement, published in 1925, irrevocably expanded the known universe beyond the confines of the Milky Way. Our galaxy was just one of countless others, each a vast collection of stars all separated by immense, incomprehensible voids of space. The universe was no longer a single island, but an archipelago of galaxies stretching out to distances previously considered impossible. Cepheid variables thus became the crucial stepping stone, the rung on the distance ladder that allowed astronomers to measure distances to nearby galaxies. They established the fundamental truth that our Milky Way was not unique, but one among billions. This paradigm shift opened the floodgates for modern cosmology, setting the stage for the discovery of an expanding universe and pushing the boundaries of the known cosmos far beyond anything Kepler or Galileo could have imagined. The universe had grown from a dome to a solar system, then to a galaxy, and now to a vast multi-galactic realm, each expansion humbling and inspiring in equal measure. But even this grand panorama was just the beginning. The rhythmic pulse of Cepheids revealed an archipelago, but the question of the entire ocean remained. The revelation that Andromeda was a galaxy in its own right, millions of light-years distant, transformed our cosmic perspective. The universe, once confined to the Milky Way, had exploded into an archipelago of island universes. This profound shift, driven by the steady pulse of Cepheid variables, initiated a new era of cosmological inquiry. The immediate question was no longer simply, how big is our galaxy? But how many galaxies are there, and how far do they truly extend? This was the dawn of extragalactic astronomy, a field pioneered by Edwin Hubble himself. Hubble, now equipped with the unparalleled light-gathering power of the 100-inch Hooker telescope, systematically began to photograph and classify the spiral nebulae that dotted the night sky. His painstaking observations revealed that many of these fuzzy patches were indeed distant galaxies, each a colossal collection of billions of stars, echoing the grandeur of our own Milky Way. He began to categorize them based on their appearance, creating the famous Hubble sequence of elliptical, spiral, and barred spiral galaxies, a morphological classification still used today. This systematic mapping, however, was only the first step. To understand the true architecture of this galactic ocean, he needed to measure their distances. Cepheid variables were the key for relatively nearby galaxies. Hubble diligently searched for these pulsating stars in other spiral nebulae, just as he had in Andromeda. Finding Cepheids in these faint distant systems was an immense challenge, pushing the limits of photographic technology and telescope aperture. Each detection was a triumph, a new beacon in the dark, unlocking another layer of the cosmos. Through these observations, he confirmed that galaxies like Triangulum, M33, and others in our local group were also millions of light-years away, systematically pushing the boundaries of the known universe farther and farther. The picture emerging was one of unimaginable scale, where galaxies were the fundamental building blocks of a far grander structure, but even Cepheids have their limits. The inverse square law dictates that light diminishes rapidly with distance. Beyond a certain point, individual Cepheid variables become too faint to resolve, even with the most powerful telescopes. To probe the truly deep universe, Hubble needed another, even brighter, standard candle. His observations, however, serendipitously provided another crucial clue. As he measured the distances to galaxies, he also measured their velocities. Working with Vesto Slipher's earlier observations of galactic redshifts, Hubble noticed a startling pattern. Slipher, almost a decade prior, had been measuring the spectra of these spiral nebulae. He observed that the light from most of them was redshifted, meaning its wavelengths were stretched towards the red end of the spectrum, much like the pitch of a siren dropping as it moves away. This Doppler shift indicated that these nebulae were moving away from Earth, and at astonishing speeds. Slipher didn't interpret this in terms of cosmic expansion, but merely as individual galactic motions. Hubble, however, would connect these two pieces of the puzzle, distance and recession velocity. In 1929, Hubble published his seminal paper, often considered the birth certificate of modern cosmology. He plotted the recession velocities of galaxies derived from Slipher's redshift measurements against their distances derived from his own Cepheid observations. The correlation was unmistakable. The farther away a galaxy was, the faster it appeared to be receding from us. This linear relationship became known as Hubble's law, mathematically expressed as v where v is the recession velocity, d is the distance, and E0, the Hubble constant, is the constant of proportionality. Hubble's law was a profound revelation. It wasn't that galaxies were simply moving through space, but that space itself was expanding, carrying the galaxies along with it. Much like dots painted on the surface of an inflating balloon, the universe was not static. As Einstein and most contemporary cosmologists believed, it was dynamic, evolving, and growing. This discovery provided the first observational evidence for a universe that had a beginning, laying the empirical foundation for the Big Bang theory. It meant the entire cosmos had been smaller, denser, and hotter in the past. The implications for cosmic distance measurement were revolutionary. Hubble's law provided a new, incredibly powerful way to estimate distances to galaxies far beyond the reach of Cepheids. If you could measure a galaxy's redshift and you knew the value of the Hubble constant, you could immediately infer its distance. Redshift, which could be measured for much fainter and more distant galaxies than individual Cepheids, became the ultimate cosmic speedometer and distance indicator for the deep universe. The value Hubble initially calculated for H0 was significantly higher than modern estimates, implying a much smaller and younger universe than we now know. This discrepancy stemmed from several factors, including the misidentification of different types of Cepheids, type 1 versus type 2, which have different period luminosity relationships, and the confusion of star-forming regions within galaxies for individual stars. Early distance measurements also suffered from the lack of knowledge about the true nature of interstellar dust, which dims distant objects. However, the principle of Hubble's law remained correct, and its impact was undeniable. Hubble's work fundamentally reshaped our understanding of the universe's size. From a few hundred light-years to a galaxy 100,000 light-years across, we had now jumped to a universe populated by billions of galaxies, stretching for hundreds of millions, even billions, of light-years. The cosmos was not just expanding, its expansion was revealing an ever greater, more intricate structure. Each new, distant galaxy discovered was a testament to this expanding vista, a new boundary pushed back in our perception of reality. The profound philosophical consequence was the final dethroning of humanity from any special cosmic location. If all galaxies were receding from each other due to the expansion of space, then there was no single center from which this expansion originated. Every observer, in every galaxy, would see the same pattern of recession. The universe was homogeneous and isotropic on large scales, looking much the same everywhere and in every direction. This cosmological principle, while conceptually unsettling to some, provided a powerful simplification for modelling the entire universe. Hubble's discovery of the expanding universe, therefore, was not just about measuring distance. It was about revealing a dynamic, evolving cosmos, one that demanded new theoretical frameworks and even more sophisticated tools to chart its ultimate scale. The Cepheids had opened the door to the galactic realm, but redshift, guided by Hubble's law, flung open the gates to the universe at large, promising to reveal its very edges, but to peer even further to the most distant reaches of time and space. Yet another, even brighter cosmic beacon would be required. The universe held more surprises, and its scale was about to be pushed to unimaginable limits. Edwin Hubble's groundbreaking work, linking galactic redshift to distance, provided the first truly universal cosmic speedometer. Yet, his initial value for the Hubble constant, while revolutionary in principle, was imprecise. This led to a perplexing conundrum. The universe, according to Hubble's early measurements, appeared to be younger than some of the oldest stars then known, a clear impossibility. The problem lay in the inherent limitations of Cepheid variables as distance indicators. While invaluable for nearby galaxies, they became too faint to observe in the most distant reaches of the cosmos, exactly where the universe's expansion dynamics were most interesting. To refine the Hubble constant and peer into the very deep past of the universe, astronomers needed an even brighter, more luminous standard candle. Enter the Type Ia supernova, cataclysmic stellar explosions that are, for a brief period, the brightest phenomena in the universe, outshining entire galaxies. These events are not just spectacularly energetic, they are remarkably consistent in their peak luminosity, making them exceptional standard candles for measuring truly immense cosmic distances. A Type Ia supernova occurs when a white dwarf star, the dense remnant of a star like our Sun, accretes matter from a companion star. As it siphons off gas, the white dwarf's mass steadily increases. If it reaches a critical mass limit, known as the Chandrasekhar limit, about 1.4 times the mass of our Sun, it becomes gravitationally unstable. The white dwarf then undergoes a runaway thermonuclear fusion reaction, igniting almost simultaneously across its entire surface, resulting in a titanic explosion. Because this critical mass limit is so consistent for all white dwarfs that undergo this specific explosion mechanism, the intrinsic brightness of a Type Ia supernova at its peak is almost identical, regardless of where it occurs in the universe. This uniformity is what makes them so invaluable. If astronomers detect a Type Ia supernova in a distant galaxy, they can compare its observed apparent brightness to its known intrinsic brightness. From this comparison, using the inverse square law of light, they can calculate the precise distance to that galaxy. This method allows astronomers to measure distances out to billions of light years, far exceeding the reach of Cepheids, which can only be seen in relatively nearby galaxies. The development of charged coupled devices, CCDs, in the 1980s, replacing photographic plates, revolutionized the detection of these elusive events. CCDs are far more sensitive to light, enabling astronomers to spot these fleeting explosions even in faint, distant galaxies. This technological leap, combined with dedicated supernova search programs, transformed Type Ia supernovae into a practical and powerful tool for mapping the far reaches of the universe. The stage was set for a monumental discovery. In the late 1990s, two independent teams of astronomers, the Supernova Cosmology Project led by Saul Perlmutter, and the High Z Supernova Search Team led by Brian Schmidt and Adam Rees, embarked on a mission to use Type Ia supernovae to measure the universe's expansion rate and its deceleration. The prevailing cosmological models, based on a universe dominated by matter, predicted that the universe's expansion should be gradually slowing down due to the collective gravitational pull of all matter within it. The more distant a supernova, the further back in time we were observing its explosion, and thus the faster the universe should have been expanding in that earlier epoch. The teams diligently observed dozens of distant Type Ia supernovae, measuring their brightness and redshifts. Their analysis was meticulous, fraught with the challenge of accounting for various confounding factors like interstellar dust, which could dim the supernovae and make them appear farther away. They developed sophisticated techniques to correct for these effects, ensuring the accuracy of their distance measurements. The results, announced in 1998, sent shockwaves through the scientific community. To the astonishment of the researchers and the entire field of cosmology, the distant supernovae were fainter than expected. This wasn't a subtle anomaly, it was a clear and consistent pattern. Fainter than expected meant they were further away than standard models predicted for their observed redshifts, and if they were further away, it meant the universe's expansion was not slowing down, as gravity should dictate. Instead, it was accelerating. This was a paradigm shift of epic proportions. The universe was not merely expanding, its expansion was speeding up, as if some mysterious repulsive force was pushing space apart. This unknown force was dubbed dark energy. The discovery of accelerating cosmic expansion, for which Perlmutter, Schmidt and Rees were awarded the Nobel Prize in Physics in 2011, dramatically reshaped our understanding of the universe's composition and its ultimate fate. It revealed that dark energy constitutes about 68% of the universe's total energy density, utterly dominating its large-scale dynamics. The impact on measuring the size of the universe was profound. Type Ia supernovae extended our observable horizon to distances of billions of light years, allowing us to map the universe's expansion history back to a time when it was only a few billion years old. By observing how the rate of acceleration changed over cosmic time, scientists could begin to constrain the properties of dark energy itself. This opened up an entirely new dimension of cosmic measurement, moving beyond just static distances to understanding the dynamic evolution of space-time. Crucially, the Type Ia supernovae method provided a far more precise value for the Hubble constant for the local universe. By combining these superluminous standard candles with Cepheid measurements for their host galaxies, astronomers could create a more accurate cosmic distance ladder. Cepheids would measure distances to nearby galaxies, which would then host Type Ia supernovae. These supernovae, calibrated by the Cepheids, would then be used to measure distances to even more remote galaxies, building a robust chain of measurements stretching across billions of light years. This multi-rung approach greatly improved the accuracy of the Hubble constant, leading to a much more consistent age for the universe that aligned with the ages of the oldest stars. The discovery of accelerating expansion fundamentally expanded our perception of the cosmos in a different, perhaps more unsettling way. It implied a universe that would continue to grow, with galaxies eventually receding beyond each other's cosmic horizons, leaving isolated island universes in an ever-darkening expanding void, getting bigger, faster, driven by a force we still barely comprehend. This era of discovery pushed our intellectual boundaries to consider not just the scale of what is, but the terrifying implications of what will be. The Type Ia supernovae had shone a light on the ultimate destiny of the cosmos, hinting at a future where even the grandest galaxies would become cosmologically alone. But to truly understand the expansion, and to probe even deeper to the very fabric of space-time and the beginning of all things, required another method entirely, one that transcended individual stars and even entire galaxies. The extraordinary discovery of accelerating cosmic expansion, fueled by the consistent brilliance of Type Ia supernovae, extended our grasp across billions of light years and revealed the universe's dynamic destiny. Yet, to truly understand the overall scale and evolution of the cosmos, we needed a more fundamental, all-encompassing measure. We needed a technique that could quantify the expansion itself, not just in localized pockets, but as a universal phenomenon stretching across the entire observable volume. This is where the concept of redshift, previously observed by Vesto Slipher and interpreted by Edwin Hubble, takes center stage as a primary cosmic ruler. Redshift, in its simplest form, is the stretching of light waves. Imagine a siren passing you. As it approaches, the sound waves are compressed, making the pitch higher, a blue shift for light. As it moves away, the sound waves are stretched, making the pitch lower, a red shift for light. For astronomical objects, a similar phenomenon occurs. When a galaxy moves away from us, the light waves it emits get stretched, shifting towards the redder end of the electromagnetic spectrum. The faster the galaxy recedes, the greater the redshift. This is known as the Doppler effect, familiar from everyday sound. However, for cosmological distances, the redshift we observe from distant galaxies is not primarily due to their physical movement through space, but rather to the expansion of space itself. As light travels across billions of light years from a distant galaxy to our telescopes, the fabric of space-time stretches. This stretching literally lengthens the wavelength of the light, making it appear redder. It's akin to drawing a wave on a rubber sheet and then stretching the sheet. The wave itself expands with the sheet. This cosmological redshift is a direct measure of how much the universe has expanded since the light left its source. The greater the redshift, the longer the light has travelled, and the more the universe has expanded in the interim, indicating a greater distance to the source. Edwin Hubble's original groundbreaking work linked this observed redshift to galactic distance, establishing his famous law. He showed that velocity, derived from redshift, was directly proportional to distance. The constant of proportionality, the Hubble constant, h0, became the linchpin for cosmological distance measurement. To measure a galaxy's redshift, astronomers use spectroscopy. They analyze the light from a distant galaxy, breaking it down into its component colors, much like a prism. Within this spectrum, they look for characteristic absorption or emission lines, unique spectral fingerprints left by specific elements like hydrogen or oxygen. By comparing the observed wavelengths of these lines to their known wavelengths in a laboratory, scientists can precisely determine how much the light has been stretched, and thus calculate the galaxy's redshift. Once the redshift, z, is measured, and assuming a value for the Hubble constant, the distance, d, can be estimated using a rearranged form of Hubble's law. This technique provides a powerful way to gauge or even type supernovae. For objects at extreme distances, redshift is essentially the only practical method for distance determination. It allows us to probe the most ancient and remote corners of the observable universe. Back to times when the first galaxies were just beginning to form, however, there's a crucial nuance. Hubble's law, as a simple linear relationship, is most accurate for relatively nearby galaxies where the expansion rate has not changed significantly over the light travel time. For very distant galaxies, we are looking back in time to an era when the universe's expansion rate was different. Before the dominance of dark energy, the universe's expansion was decelerating due to the gravitational pull of matter. Then, approximately 5 to 6 billion years ago, dark energy began to dominate, causing the expansion to accelerate. This complex expansion history means that for the most distant objects, the simple Hubble's law needs to be refined by sophisticated cosmological models that account for the changing expansion rate over cosmic time. These models incorporate our understanding of dark matter and dark energy, allowing us to convert an observed redshift into a look-back time and a precise co-moving distance, the distance between two objects if the universe's expansion were to stop at this instant. The development of increasingly sensitive spectrographs on ground-based telescopes and space observatories has allowed astronomers to measure redshifts for millions of galaxies. Large-scale galaxy surveys, such as the Sloan Digital Sky Survey, SDSS, and the Dark Energy Spectroscopic Instrument, DESI, have meticulously mapped the distribution of galaxies across vast swathes of the sky, creating stunning three-dimensional maps of the cosmic web. Each galaxy in these maps is placed at its proper cosmological distance, primarily determined by its redshift. These surveys reveal not just individual galaxies, but the grand architecture of the universe, colossal clusters, vast filaments, and enormous seemingly empty voids, structures spanning billions of light years. The consistency of redshift measurements with the cosmic distance ladder, parallax calibrating Cepheids, Cepheids calibrating type Ia supernovae, and type Ia supernovae calibrating Hubble's law, is a testament to the robustness of our cosmological models. However, the exact value of the Hubble constant, h0, remains a source of significant tension in modern cosmology. Measurements derived from observations of the local universe, using Cepheids and type Ia supernovae, consistently yield a higher value for h0, around 73 km s MPC, than those derived from observations of the very early universe, such as the cosmic microwave background, which we will discuss later, which suggest a lower value, around 67 km s MPC. This Hubble tension represents a profound paradox, indicating a potential crack in our standard cosmological model, or an unknown local influence on our measurements. Despite this ongoing challenge, redshift remains the ultimate tool for pushing the boundaries of the observable universe. It allows us to glimpse light from galaxies so distant that their light left them when the universe was only a few 100 million years old, just as the first stars and galaxies were forming. These are the highest redshift objects, appearing as faint, stretched-out smudges of light, their photons having embarked on an epic journey across nearly the entire history of the cosmos. By measuring these extreme redshifts, astronomers can determine the edge of the observable universe. This isn't a physical edge in space, but a horizon in time. We can only see as far back as the universe has been transparent to light. Beyond a certain redshift, the universe was so hot and dense that light could not travel freely. It was trapped in a primordial plasma. The light from that epoch forms the cosmic microwave background, which represents the ultimate limit of what we can see with photons. Redshift, therefore, transformed static, local entity to a dynamically expanding cosmos. Stretching for tens of billions of light years, it provided the first real glimpse into cosmic history, allowing us to reconstruct the timeline of expansion and the formation of large-scale structures, from the relatively small distances measured by parallax to the vast redshift-determined reaches of the early universe. Humanity had truly begun to comprehend the almost unimaginable scale of its cosmic home, expanding, a living, breathing entity whose size was constantly evolving. But to truly grasp its full extent, and to anchor the redshift measurements in the primordial past, we needed to look at the oldest light of all. The cosmological redshift, as a universal speedometer for the expanding cosmos, allowed us to chart the vast distances to billions of galaxies, pushing our observational horizon back to the universe's infancy. Yet, to fully understand the universe's expansion history and to anchor these immense distances, cosmologists needed a standard ruler that was imprinted on the very fabric of the early universe. Something that existed before galaxies, before stars, a pristine measuring stick from the Big Bang itself. This is precisely what Baryon Acoustic Oscillations, or BAOs, provide, a cosmic ruler born from primordial sound waves. Imagine the early universe, just a few 100,000 years after the Big Bang. It wasn't the cold, dark vacuum we know today, but a superheated, dense plasma, a cosmic soup of protons, electrons, photons, and dark matter. In this plasma, intense pressure from photons pushed matter outward, while gravity from concentrations of dark matter pulled it inward. This cosmic tug-of-war created sound waves, much like ripples in a pond, propagating through the plasma. These sound waves were not merely vibrations, they were oscillations in the density of matter and radiation, expanding outward from initial overdensities. For approximately 380,000 years, light and matter were inextricably coupled. Photons, constantly scattering off free electrons, effectively dragged the baryonic matter, normal matter like protons and electrons, along with them. This process created expanding spheres of slightly denser baryonic matter, with dark matter at their centers providing the gravitational anchor. Then, a pivotal moment arrived: recombination. The universe cooled sufficiently for electrons and protons to combine, forming neutral hydrogen atoms. This event made the universe transparent to light. Suddenly, the photons were free to travel unimpeded, decoupling from matter. The sound waves, which relied on the tight coupling of light and matter, effectively froze in place. The crucial consequence of this freezing was that the spheres of baryonic matter, which had been expanding outward at the speed of sound for 380,000 years, left a distinct imprint. The distance these sound waves travelled before freezing created a preferred scale, a characteristic bubble size in the distribution of matter. This scale, imprinted in the early universe, translates to a physical distance of approximately 490 million light-years in the modern universe. This characteristic distance acts as a standard ruler. Just as a carpenter uses a fixed-length ruler to measure a building, astronomers use the BAO scale to measure the universe. When we look out at the large-scale distribution of galaxies today, we find that galaxies are not randomly scattered. They tend to cluster together, but with a subtle, statistically significant preference for pairs of galaxies to be separated by this precise BAO distance. It's like finding a universal cosmic fingerprint left by the Big Bang. To detect this subtle signal, astronomers undertake monumental galaxy surveys, projects like the Sloan Digital Sky Survey, SDSS, the Wigglesy Dark Energy Survey, and the Baryon Oscillation Spectroscopic Survey, BOSS, have meticulously mapped the three-dimensional positions of millions of galaxies across billions of light-years. By analysing the statistical clustering of these galaxies, they can identify the faint but clear signature of the BAO scale. This is a formidable task, requiring sophisticated statistical techniques to sift this primordial signal from the noise of random galaxy distributions and local gravitational effects. Once the Bayer scale is measured at different redshifts, and thus different distances and different epochs in cosmic history, it becomes an incredibly powerful tool for mapping the universe's expansion. By comparing the apparent angular size of this standard ruler at various distances to its known physical size, scientists can determine how much space has expanded since the light left those galaxies. If the universe's expansion has accelerated or decelerated in a particular way, it will affect how large or small this ruler appears to us over cosmic time. The Bayer method provides a purely geometric way to measure distances, largely independent of the complexities that can affect other standard candles, such as dust extinction or evolutionary effects in stars. It relies on well-understood physics from the early universe and the statistical distribution of matter, offering an exceptionally robust and precise method for charting the large-scale structure and expansion history of the cosmos. Bayers have played a critical role in confirming the existence of dark energy and refining our understanding of its properties. By measuring the Bayer scale at different redshifts, astronomers have observed a consistent pattern of expansion that directly supports the accelerating universe discovered with Type Viré supernovae. Moreover, BAOs provide a crucial cross-check for the Hubble constant, offering an independent way to measure the expansion rate of the universe, particularly when looking at vast cosmic scales. The BAO measurements, derived from the very early universe, tend to align with the lower value of the Hubble constant, around 67 km/s MPC, contributing significantly to the ongoing Hubble tension when compared to local measurements. The significance of Baryon Acoustic Oscillations cannot be overstated. They represent a remarkable triumph of modern cosmology, allowing us to connect the microscopic quantum fluctuations in the early universe to the grand, foam-like structure of the cosmic web we observe today. These ancient sound waves, frozen in time, provide a direct universal ruler that helps us map the universe's geometry, its expansion rate, and its composition across billions of light years. They allow us to peer back to an era when the universe was only a few % of its current age, providing a fundamental anchor for the entire cosmic distance ladder. With each new survey, mapping tens of millions of galaxies with even greater precision, BAOs continue to refine our cosmic map. Future instruments like the Dark Energy Spectroscopic Instrument DESI and the Euclid Space Telescope are designed specifically to enhance BAO measurements, promising to reduce uncertainties in the Hubble constant and shed further light on the nature of dark energy. The universe, once an unmeasurable expanse, is now being charted with ever-increasing precision, thanks to the subtle yet profound echoes of its earliest moments. This ancient sound wave has become one of our most powerful tools for defining the true scale and history of the cosmos, taking us to the very edge of the observable. Baryon Acoustic Oscillations provide a powerful ancient ruler to map universe. Yet, even this technique, which charts the distribution of galaxies across billions of light years, relies on observing actual galaxies. But what if we could peer beyond the galaxies themselves to the very moment the universe became transparent, to the earliest light that could ever reach us? This is the domain of the cosmic microwave background, or CMB, the faint afterglow of the Big Bang, representing the ultimate observational frontier and the deepest measure of cosmic distance. Imagine the universe not as it is today, but as it was 13.8 billion years ago, a mere 380,000 years after the Big Bang. At this primordial epoch, the cosmos was a superheated opaque fog, a plasma so dense and energetic that electrons and protons could not combine to form stable atoms. Light, in the form of photons, was constantly scattering off these free electrons, unable to travel more than a tiny distance before being reabsorbed or deflected. The universe was effectively opaque, like being inside a thick cloud. As the universe continued to expand, it also cooled. When the temperature dropped to approximately 3 Kelvin, about 2,700 degrees Celsius, a critical threshold was crossed. Electrons and protons finally combined to form stable, neutral hydrogen atoms. This event, known as recombination or decoupling, marked a pivotal moment in cosmic history. With the free electrons now bound within atoms, the photons were no longer constantly scattering. The the universe suddenly became transparent to light. These liberated photons, having travelled freely ever since, are what we detect today as the cosmic microwave background. This ancient light is the oldest observable phenomenon in the universe, a direct relic from its infancy. It reaches us from every direction in the sky, a pervasive faint microwave glow. Originally, these photons were emitted as intense visible and ultraviolet light, but over 13.8 billion years of cosmic expansion, their wavelengths have been stretched dramatically, redshifting them into the microwave part of the electromagnetic spectrum. This extreme redshift makes the CMB a unique and unparalleled tool for probing the universe at its earliest observable moments. The discovery of the CMB was serendipitous. In 1964, Arno Penzias and Robert Wilson, engineers at Bell Labs, detected a persistent, annoying hiss in their horn antenna that they couldn't eliminate. After meticulously ruling out every terrestrial source, including pigeon droppings, they realized they had stumbled upon a fundamental cosmic signal. Unbeknownst to them, Princeton physicists Robert Dicke, James Peebles, and others had independently predicted the existence of this afterglow. Penzias and Wilson had, quite literally, heard the echoes of the Big Bang, an observation that provided overwhelming evidence for the hot Big Bang model of cosmology. While the CMB is remarkably uniform in temperature, about 2.725 Kelvin, satellites like the Cosmic Background Explorer, COBE, the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck spacecraft have revealed incredibly subtle variations in its temperature, differences of only a few parts per 100,000. These tiny anisotropies, or hot and cold spots, are not random noise. They are the fossilized imprints of primordial density fluctuations in the early universe, the very seeds from which all large-scale structures, galaxies, galaxy clusters, and the cosmic web eventually grew. The angular scale and statistical properties of these hot and cold spots on the CMB map encode a wealth of cosmological information. They contain signatures of the same sound waves that give rise to Baryon Acoustic Oscillations, but observed at an even earlier epoch before galaxies had even formed. By analysing these patterns, cosmologists can precisely determine fundamental parameters of the universe, including its age, its geometry, whether it's flat, open, or closed, and the relative proportions of ordinary matter, and dark energy. For our quest to measure the size of the universe, the CMB is paramount. It acts as a kind of cosmic horizon, the furthest back in time we can see with light. The light from the CMB has been travelling for 13.8 billion years. This means the universe was 13.8 billion light-years big in terms of light travel distance when that light was emitted. However, because the universe has been continuously expanding during that journey, the physical distance to the source of the CMB photons today is far greater. This is where the concept of co-moving distance becomes critical. Using the CMB data, particularly from the Planck mission, cosmologists have precisely constrained the universe's expansion history. They can run sophisticated cosmological models backward and forward in time, calculating how much space has expanded between the emission of the CMB photons and their reception today. These calculations reveal that the actual distance to the source of the CMB, considering the expansion of space, is approximately 46.5 billion light-years in every direction. This defines the radius of our observable universe. The CMB also provides an independent and highly precise measurement of the Hubble constant. Because it reflects the universe's expansion rate in its very early stages, the CMB-derived Hubble constant, around 67 km as MPC, represents the global expansion rate, averaged over the entire cosmos and its early history. This is in stark contrast to the local measurements from Cepheids and supernovae, which yield a higher value, giving rise to the persistent Hubble tension. The CMB, therefore, not only defines the outer limits of our visual perception, but also highlights a profound discrepancy in our understanding of the universe's expansion, a paradox that challenges the very consistency of our cosmic models. In essence, the cosmic microwave background is more than just a picture of the baby universe. It is the ultimate standard ruler and clock, providing the foundational data to understand the universe's geometry, age, and ultimate scale. It is the furthest point on our cosmic distance ladder, representing the boundary of what we can directly observe with photons, from the intimate scale of parallax to the galactic spans of Cepheids. the intergalactic reach of supernovae, and the large-scale patterning of BAOs, the CMB finally gives us a full, albeit still paradoxical, picture of our truly immense and evolving cosmos. It tells us not just how far we can see, but how old everything is, and how much space has stretched in the interim, revealing a universe far larger and more intricate than any prior era could have fathomed. The cosmic microwave background provides a definitive boundary to what we can see in the universe. It is the light from the universe's earliest transparent moments, effectively a sphere of last scattering around us. But to fully grasp the real size of the observable universe, we must understand that the light we receive today from the CMB has travelled for 13.8 billion years through an ever-expanding cosmos. The universe has not stood still during that journey. It has continued to stretch and grow. Therefore, the objects that emitted that ancient light are now much, much farther away than a simple light travel distance of 13.8 billion light-years would suggest. This distinction is crucial. Light travel distance versus co-moving distance. The light travel distance is straightforward. It's how long the light has been travelling to reach us. But because space itself expands, the actual physical separation between us and the source of that light has increased dramatically over cosmic time. Imagine a tiny ant crawling on an inflating balloon. The ant travels a certain distance on the surface, but the points on the balloon's surface are moving away from each other as the balloon inflates. The co-moving distance is essentially the distance we would measure today if we could instantly stop the expansion of the universe and stretch a giant cosmic ruler from our location to the source of that ancient light. To calculate this co-moving distance, cosmologists employ sophisticated models based on Einstein's theory of general relativity, incorporating our best understanding of the universe's composition, the precise amounts, as determined by observations like the cosmic microwave background and type Millennia supernovae. These models allow us to reconstruct the universe's expansion history, detailing how rapidly space expanded at different epochs since the Big Bang. By integrating this expansion history from the time the CMB light was emitted to the present day, we can calculate the current physical distance to the edge of what we can observe. The result of these calculations is staggering. The radius of the observable universe, the distance from Earth to the furthest detectable light, is approximately 46.5 billion light-years. This means that the entire observable universe, our cosmic sphere of perception, spans roughly 93 billion light-years in diameter. This number is not an arbitrary figure. It is a direct consequence of the universe's age, its expansion rate, and its composition. It represents the maximum extent from which light has had enough time to reach us since the Big Bang, accounting for the continuous stretching of space during its journey. To truly contextualize this scale, let's consider the hierarchical structure within this immense sphere. At the smallest familiar scale, we have our solar system, mere light hours across. Our Milky Way galaxy spans about 100,000 light-years, a colossal collection of hundreds of billions of stars. The local group, our immediate galactic neighbourhood, containing Andromeda and dozens of smaller galaxies, extends for roughly 10 million light-years. Beyond that, the Laniakea supercluster, a vast gravitational basin housing over 100,000 galaxies, stretches for about 500 million light-years. These are all individual threads within the larger cosmic tapestry, itself spanning billions of light-years. This observable universe, with its 93 billion light-year diameter, is structured in a vast, foam-like network known as the cosmic web. This web consists of dense clusters of galaxies, long filaments of galaxies connecting these clusters, and enormous, relatively empty regions called cosmic voids. Our Milky Way, along with the entire local group and Laniakea supercluster, is just one tiny node within this intricate grand-scale architecture. The largest structures identified within this observable expanse, such as the Hercules Corona Borealis Great Wall, span as much as 10 billion light-years, emphasizing the truly enormous scale of cosmic organization. It's important to clarify that observable does not mean all there is. The observable universe is simply the portion of the cosmos from which light has had time to reach us. Because the universe is expanding, and because the speed of light is finite, there are undoubtedly regions of space beyond our observable horizon. These regions existed in the past and they exist now, but their light has not yet had enough time to travel to Earth. We cannot see them, and by definition, we cannot measure them directly. Their existence is inferred from the uniformity and flatness of the observable universe, suggesting that the cosmos extends far beyond what our telescopes can ever detect. The concept of the edge of the observable universe is therefore a temporal and perceptual boundary, not a spatial one. There is no physical wall or barrier. If we were situated in another galaxy far across the cosmos, we would have our own observable universe, a sphere of identical radius centered on that galaxy. The universe is likely far vaster, perhaps even infinitely large, but our perception is limited by the age of the universe and the speed of light. Moreover, the current size of the observable universe is not static. Due to the ongoing acceleration driven by dark energy, the boundary of our observable universe is slowly shrinking in terms of which objects we can causally interact with. Distant galaxies are not only receding from us, but the space between us and them is expanding faster and faster. Eventually, many currently observable galaxies will cross an event horizon, beyond which their light will never reach us, regardless of how long we wait. The 93 billion light-year diameter is a snapshot, a current measure in an ever-evolving cosmos. The precise measurements leading to this number are a culmination of all the techniques we've discussed: parallax for local calibration, Cepheids for galactic and nearby extragalactic distances, type Ia supernovae for the deeper universe and its expansion history, redshift for the most distant galaxies, and Baryon Acoustic Oscillations for tracing the cosmic web. Each method builds upon the last, forming a robust, albeit still refined, cosmic distance ladder. This ladder is anchored at its base by direct geometric measurements and stretches to the farthest reaches of time and space through increasingly sophisticated astrophysical insights and cosmological models. The current 93 billion light-year measurement represents a profound triumph of human intellect and scientific collaboration. It's a number that forces us to reconsider our place, not just in our solar system or our galaxy, but within the vast, awe-inspiring immensity of the cosmos. It's a testament to how far we've come from the geocentric dome, and a powerful reminder of how much more there is to discover beyond the limits of our current perception. The observable universe is our current cosmic sandbox, but the universe itself is almost certainly a beach stretching into infinity. The 93 billion light-year diameter we have meticulously charted represents the observable universe, a colossal sphere centered on Earth, defined by the furthest reach of light since the Big Bang. But this is not the universe itself, merely the portion we can perceive. It is our cosmic horizon, a limit imposed by the finite speed of light and the universe's finite age. To mistake this observational boundary for the entirety of existence would be to repeat the geocentric error on a grander scale, confining an infinite possibility to our limited view. The true size of the cosmos, the universe beyond our sight, may be unimaginably vaster, perhaps even genuinely infinite. The very geometry of space offers a profound clue to this unseen immensity. Data from the cosmic microwave background, particularly from the Planck satellite, reveals that the universe is remarkably flat. This isn't flat in a two-dimensional sense, but geometrically flat in 3 dimensions, meaning that parallel lines remain parallel, and the sum of angles in a triangle is exactly 180 degrees. While a flat universe could technically be finite, current cosmological models strongly suggest that a universe this flat, extending so uniformly in every direction, almost certainly implies an infinite expanse. If the universe truly extends without end, then the observable sphere is just a single, contained bubble within an endless, replicating cosmic ocean. Beyond the visible light of the CMB lies a fundamental barrier, the cosmic horizon. This isn't a physical wall, but a temporal boundary. Light from before, the universe cooled enough to become transparent, simply hasn't reached us, and fundamentally cannot reach us through photons, because it was trapped in the primordial plasma. Furthermore, due to the accelerating expansion driven by dark energy, there are galaxies currently within our observable universe that are already receding from us faster than the speed of light. Their light may still reach us for a time, having been emitted when they were closer, but eventually even these objects will cross an event horizon, their future light forever unable to bridge the ever-increasing gulf of space. The observable universe, far from being static, is a dynamic, evolving boundary constantly shifting as space expands and time progresses. This concept of an infinite universe opens the door to even more mind-bending possibilities, notably the multiverse. If space-time stretches infinitely, then every possible arrangement of matter and energy must eventually repeat. Given enough space, exact copies of our galaxy, our solar system, even ourselves, could exist an unfathomable distance away. This Level 1 multiverse arises directly from the idea of infinite space. But there's an even grander, more speculative, Level 2 multiverse concept rooted in the theory of eternal inflation. During the Big Bang, a period of exponential expansion called inflation is thought to have occurred. If this inflation never truly stops everywhere, but only ends in localized bubbles, then our universe is just one such bubble. Each bubble could have different physical constants, different particles, and even different dimensions, making for an endless array of distinct universes, constantly budding off from a perpetually inflating parent spacetime. The grand architecture of the cosmic web, with its vast filaments and enormous voids, further complicates our understanding of cosmic scale. While the cosmological principle asserts that the universe should be homogeneous and isotropic on sufficiently large scales, meaning it looks roughly the same everywhere and in every direction, the detection of structures like the KBC void, a colossal underdense region 2 billion light-years across where we happen to reside, challenges this assumption. If our local environment is genuinely anomalous, if we live in a special place by chance, then our measurements of the universe's expansion or its overall properties might be subtly biased. This would suggest that to truly grasp the universe's average behavior, we need to look even further than we currently do, or perhaps account for our unusual vantage point in ways we haven't fully mastered. Indeed, the most persistent paradox in our cosmic measurement toolkit, the Hubble Tension, underscores this uncertainty. The discrepancy between the universe's expansion rate, measured from the local cosmos, using Cepheids and supernovae, and the rate inferred from the ancient cosmic microwave background is a critical unresolved puzzle. This 9% difference, far too significant to be dismissed as mere error, hints at either new, unknown physics operating in the early universe, or a systematic bias in our local measurements due to our immediate cosmic environment. The void hypothesis offers one compelling explanation, suggesting our measurement is accelerated by local gravitational flows, but until this tension is resolved, it leaves a fundamental question mark over the absolute scale and evolution of the universe, challenging the very bedrock of our standard cosmological model. Our current understanding also grapples with the invisible majority of the cosmos, dark matter and dark energy. These enigmatic components make up about 95% of the universe's total mass-energy content, yet their true nature remains unknown. Dark matter, which provides the gravitational scaffolding for galaxies and clusters, profoundly influences the formation and distribution of structures across billions of light-years. Dark energy, the mysterious repulsive force, dictates the universe's accelerating expansion, shaping its ultimate fate and the rate at which its scale grows. Without a complete understanding of these dominant constituents, our models of cosmic evolution, and thus our measurements of its true scale, remain inherently incomplete, built upon a foundation largely unseen. The journey to measure the universe has been a continuous process of confronting the limits of our perception and the boundaries of our knowledge. Each new method, from parallax to redshift, pushed back the known world, only to reveal new layers of mystery. From a tiny, Earth-centered dome, we've expanded our understanding to an observable sphere, 93 billion light-years across, teeming with billions of galaxies. Yet, this incredible triumph of science simultaneously reveals our intellectual humility. We are still peering through a cosmic window, limited by the speed of light and the age of time. The questions that remain about the universe beyond our horizon, the nature of dark energy, the resolution of the Hubble tension, and the potential for a multiverse remind us that the greatest discoveries may still lie beyond our current grasp. Perhaps the ultimate truth of the universe's size transcends simple numerical figures. What if distance itself is an emergent property of a deeper, more fundamental reality? What if our three spatial dimensions are merely a small part of a larger folded tapestry of space-time, where other dimensions remain hidden? These are not questions for tomorrow, but for centuries hence, a testament to the enduring human spirit of inquiry. Our measurements are maps, and like all maps, they are imperfect representations of an infinitely grander reality. To truly comprehend the real size of the universe is not just to quantify its scale, but to embrace the infinite unknown that lies just beyond our grasp, forever inviting us to look deeper, to question further, and to wonder at the boundless cosmos. Our odyssey through the cosmic scales has traced an intellectual journey spanning millennia, a testament to humanity's unyielding drive to comprehend its place within the vastness. We began with a universe no larger than a few thousand miles, a snug, geocentric dome where Earth reigned supreme, and stars were mere pinpricks on a crystal sphere. Each measurement, each new cosmic yardstick we painstakingly crafted, peeled back a layer of this comforting illusion, propelling us outwards from our familiar terrestrial home, past the Sun, through our own magnificent galaxy, and into an unimaginable ocean of other galaxies, from the delicate wobble of stellar parallax which first quantified interstellar space, to the rhythmic pulse of Cepheid variables, which revealed our Milky Way as but one island among billions, to the explosive brilliance of Typeia supernovae that unveiled the universe's accelerating expansion, and the universal stretch of redshift that mapped its grandest structures. Every step was a monumental leap. The precision offered by Baryon Acoustic Oscillations, frozen sound waves from the universe's infancy, provided a truly universal ruler, connecting the microscopic quantum fluctuations of the Big Bang to the colossal cosmic web we inhabit. And finally, the faint, pervasive whisper of the cosmic microwave background, the oldest light in existence, established the definitive boundary of our observable universe, a sphere stretching 93 billion light-years across. This is not merely a collection of facts or numbers, it is a profound narrative of human intellectual evolution, a chronicle of how our tools, our minds, and our very philosophies have had to expand to accommodate a cosmos far more intricate and awe-inspiring than our ancestors could ever have dreamed. This relentless pursuit of cosmic scale has instilled in us a profound sense of humility. We are not at the centre, nor are we unique. Our planet is one of countless worlds orbiting one of billions of stars in one of billions of galaxies. This descent from cosmic centrality, however, is not a diminishment but an elevation. It reveals the extraordinary capacity of the human mind, born from the dust of a single star, to comprehend, to measure, and to theorize about the entirety of existence. It is a testament to the power of scientific inquiry, a method that, through rigorous observation and intellectual honesty, continually reshapes our understanding of reality, even when those realities are uncomfortable or counterintuitive. Yet, even as we celebrate these triumphs, our cosmic map remains incomplete, punctuated by vast stretches of the unknown and riddled with persistent paradoxes. The 93 billion light-year observable universe is a sphere of perception, universe's finite age. Beyond this horizon, the universe almost certainly stretches further, perhaps infinitely. Our flat cosmic geometry, a revelation from the CMB, strongly hints at an endless expanse, a boundless tapestry where matter and energy configurations may repeat, giving rise to the mind-bending concept of a level 1 multiverse. If true, then every event, every history, every version of ourselves could exist somewhere, an infinite distance away, making our observable bubble just one tiny, precious iteration in an endless cosmic array. But the mysteries are not confined to the unobservable. Even within the realms we can probe, fundamental tensions persist. The Hubble Tension, the nagging discrepancy between local and global measurements of the universe's expansion rate, remains a profound challenge to our standard cosmological model. Is it an indication of new physics, a subtle flaw in Einstein's gravity on cosmic scales, or simply a local bias caused by our unusual position within a cosmic void? The KBC void, the immense underdense region where our galaxy happens to reside, offers a compelling, albeit philosophically unsettling explanation. If our cosmic neighbourhood is indeed a statistical anomaly, it forces us to reconsider the cosmological principle, the bedrock assumption of uniformity that underpins much of our cosmic understanding. It implies that our perspective, no matter how precise our instruments, might be skewed, making the universe lie to us about its fundamental properties. This is a crisis of interpretation, a call to push the boundaries of observation and theory even further. Then there is the invisible majority, dark matter and dark energy, the architects of cosmic structure and the drivers of its accelerating fate. We can measure their effects with astonishing precision, but their true nature remains shrouded in mystery. They are the scaffolding and the engine of the cosmos, yet they remain dark, elusive, challenging our most fundamental theories of particle physics and gravity. Our current cosmic map is largely a map of the unknown, a testament to the fact that we have only just begun to truly understand the constituents of reality. How can we fully grasp the real size of something whose fundamental composition largely eludes us? These are the profound questions that tantalize the next generation of cosmic cartographers. The journey to measure the universe is therefore an endless one. Each solved mystery invariably reveals new, deeper questions. The expansion of our scientific understanding of cosmic scale is a mirror to the expansion of the universe itself, constantly growing, always revealing more, never truly reaching a final static state. This relentless pursuit is not just about numbers. It's about the very nature of existence, our place within it, and the limits of human knowledge. It is a dialogue between humanity and the cosmos, a conversation that began with a curious gaze and continues with ever more sophisticated instruments and theories. We stand at a unique moment in cosmic history, able to witness the universe in its full, structured grandeur, with its intricate cosmic web of galaxies, filaments, and voids. Billions of years from now, as dark energy continues its relentless work, this structure will dissipate, galaxies will recede beyond causal horizons, and the universe will become an even emptier, darker place. Future civilizations, if they exist, might find themselves in profound cosmological isolation, unable to observe the distant signals that currently allow us to reconstruct the Big Bang and map the accelerating expansion. We are, in a sense, privileged observers, living in an era when the universe's story is still legible, its grand narrative still unfolding before our eyes, to grasp, quote, a number like 93 billion light-years. It is to internalize the journey of discovery, the intellectual battles fought, the paradigms shattered, and the profound questions that continue to echo across the cosmos. It is to appreciate the intricate dance of light, gravity, and space-time that allows us to even ask such questions. It is to accept that the universe remains far stranger, far grander, and far more mysterious than we can currently imagine. Our instruments may reach the observable edge, but the universe itself invites an endless journey of the mind, a perpetual quest for understanding that lies at the very heart of what it means to be human. The cosmos is not just big, it is an eternal invitation to wonder,